Thank you very much for the introduction and for the opportunity to present my work here. So in this theoretical talk, I will describe how one can realize anionic edge interferometry in phonon-coupled Kitaev spin liquids using currently available thermal transport techniques. Before I start my talk, let me thank my collaborators on this project, Kai Klocki and Joel Moore from Berkeley, as well as Jason Alisa from Caltech, and let me also acknowledge the Quantum Science Center for supporting my research. So I guess this audience doesn't need a lengthy introduction to quantum spin liquids, but just for completeness, quantum spin liquids are fundamentally quantum phases of magnetic insulators that, in contrast to conventionally ordered magnets, are not characterized by a classical long-range order, but instead by a long-range quantum entanglement that gives rise to a rich variety of interesting emergent phenomena. The fundamental spin degrees of freedom fractionalize into a bunch of non-local quasi-particle excitations that in general exhibit non-trivial anionic particle statistics. They are neither bosons nor fermions, but something beyond this conventional dichotomy. And in the case of gapped spin liquids, we also have a topological order and an associated topological ground state degeneracy that is protected against arbitrary local perturbations. So arguably these days, the most well-studied quantum spin liquid is the Kitaev spin liquid. And this spin liquid phase is of specific importance because on the one hand, it is believed to be relevant for a bunch of experimental materials, the honeycomb iridates and alpha ruthenium chloride, for example. And on the other hand, it also has a nice exactly solvable limit, where it is described by the famous Kitaev honeycomb model, which is exactly solvable and thus allows for more in-depth theoretical investigations. So what we learned from the exact solution is that the ground state of the Kitaev honeycomb model is a gapless spin liquid, the Kitaev spin liquid, in the absence of a magnetic field. And this spin liquid has two kinds of fractionalized quasi-particle excitations. There are the gauge fluxes, which are localized at these hexagonal plaquettes and are gapped. And then there are the Majorana fermions, which are delocalized and are gapless at a finite number of Dirac points, with their dispersion being precisely identical to that of electrons in graphene. So perhaps most interestingly, if one applies an infinitesimally small magnetic field, thereby breaking time reversal symmetry, then these Majorana fermions are immediately gapped out and form topologically non-trivial bands with finite Chern numbers. At the same time, the gauge fluxes that were gapped to start with acquire non-Abelian particle statistics, and they become non-Abelian Ising anyons. And it is because of the presence of these non-Abelian anyons that this new gapped phase that one gets from the gapless Kitaev spin liquid by applying a magnetic field is called non-Abelian Kitaev spin liquid. And this phase is going to be the focus of the rest of this talk. So from a more abstract perspective, the non-Abelian Kitaev spin liquid can be thought of as a topologically ordered phase. And the topologically ordered phases in general are characterized by their topologically distinct anyon types, as well as the various fusion and braiding rules between these different anyon types. So for the non-Abelian Kitaev spin liquid, there are three kinds of distinct anyons. There is the trivial boson, which is basically like a simple particle, not an anyon at all, which is denoted commonly by 1. Then there is the Majorana fermion, denoted by psi, and the Ising anyon, denoted by sigma. These are the actual non-trivial anyons. And then what do I mean by topologically distinct anyons? So two anyons are topologically distinct. If one cannot turn one into another by just doing some kind of local operations, the only way I can change the type of an anyon is to bring in another anyon from far away and fuse it with the first anyon. And that's precisely what the fusion rules tell us. If I have two anyons, I combine them, what kind of anyon do I get as a result? So for example, in the non-Abelian Kitaev spin liquid, if a fusion of two Majorana fermions gives a trivial boson, fusion of an Ising anyon with a Majorana fermion gives an Ising anyon, while fusion of two Ising anyons may either give a trivial boson or a Majorana fermion. Now, the presence of two distinct fusion channels for the fusion of two Ising anyons tells us that these Ising anyons are non-Abelian anyons. So a pair of well-separated Ising anyons supports a non-trivial internal Hilbert space of dimension 2, a topological qubit if you wish, that has two states that are almost perfectly degenerate up to exponential accuracy in the distance of the Ising anyons. And finally, the braiding rules tell us what happens to the underlying quantum state if I take one anyon and I move it around another anyon. So for example, in the non-Abelian Kitaev spin liquid, if I take a Majorana fermion and I move it around an Ising anyon, the underlying quantum state is multiplied by a non-trivial phase vector -1. And finally, by virtue of the usual bulk-edge correspondence of topological phases, the topologically non-trivial bulk of the non-abelian Kitaev spin liquid translates into a topologically non-trivial edge. And in particular, the edge of the non-abelian Kitaev spin liquid supports a chiral-Majorana edge mode that facilitates the unidirectional transport of Majorana fermions all the way around the edge. And in general, a key property of any chiral edge mode is the chiral central charge, which basically tells us how many degrees of freedom are transported along the edge. And in general, for the simplest kind of topological phases, like integer quantum Hall states, that chiral central charge would be an integer. But for the non-abelian Kitaev spin liquid, it's actually takes a fractional value c equals 1/2. And this fractional nature of the chiral central charge is extremely important because, again, by the bulk edge correspondence, it directly reflects the fact that the bulk of the system supports non-abelian anyons. And this half-integer chiral central charge is also what translates into the half-integer quantized thermal Hall conductivity that was recently observed in the candidate material alpha ruthenium chloride. Again, I'm sure most of you are very much familiar with these experiments, and also Professor Takagi gave a nice overview on Monday, so I'm going to be very brief here. But the main point is that in this 2018 paper, Yuji Masuda's group in Japan measured the thermal Hall conductivity of alpha ruthenium chloride in a magnetic field. And what they found is that in a temperature range roughly between 3 and 6 kelvins, and also for in-plane magnetic fields roughly between 8 and 9 teslas, the thermal Hall conductivity takes a half-integer quantized value that one would expect from the non-abelian Kitaev spin liquid. Which is very nice, but of course, as you all know, many other groups were unable to reproduce these results. There are lots of issues with the sample dependence. There are different kind of competing interpretations. The situation is highly controversial. So it is clear that even more direct evidence of anyons in the non-abelian Kitaev spin liquid is required. And one very promising direction to consider, motivated by electronic topological phases like quantum Hall systems, is the idea of anyonic edge interferometry that can directly probe the braiding rules, braiding properties between different types of anyons. So in the context of quantum Hall systems that have chiral electron edge modes rather than chiral Majorana edge modes, one can consider, for example, this setup as a very old paper. One puts a whole bar in between a source and the drain, and then one measures the electrical conductance between the source and the drain. Now, the bulk is gapped for electrons, so the only place where the electron can jump in from the source if one applies a voltage is at the edge. And if there are no constrictions here in the middle, then the electron will go straight to the drain, and then the measured conductance will be just some number times E squared over H. Now, if there is a constriction in the middle, then this electron flowing down here can actually jump over to the opposite edge and go back to the source instead of going to the drain, in which case, of course, the measured conductance between source and drain will be smaller. Now, if there are two constrictions, then the electron can jump over at either constriction, and these two processes can, in general, interfere. And then, depending on the nature of this interference, whether it's constructive or destructive, the measured conductance between source and the drain will be smaller or larger, respectively. So in the case of the simplest integer quantum Hall states, only electrons can jump here, and then what controls the nature of this interference is entirely this magnetic flux here. So as a function of changing this magnetic flux, one obtains Aharonov-Bohm oscillations of the conductance, because the interference of electrons happens via the Aharonov-Bohm effect. Now, if one takes a fractional quantum Hall state instead, then in addition to electrons jumping, anyons with fractional charge can also jump here. And these anyons are not only sensitive to the total magnetic flux here, but also to any bulk anyons that may be residing in this central region between the two constrictions. And if one could somehow localize an anyon here, that would show up in a shift of the Aharonov-Bohm oscillations as a function of the magnetic flux, as was observed recently in very beautiful experiments by Mike Mumford's group at Purdue University. So, of course, this setup on its own does not directly apply to chiral quantum spin liquids like the non-abelian Kitaev spin liquid, because, of course, spin liquids are Mott insulators, so one cannot just apply an electrical current. However, by the chiral Majorana edge mode that there is in a chiral quantum spin liquid carries no charge, it still carries energy, so it's a very natural direction to think about, that one can think of some kind of thermal analog of this setup, where instead of applying an electrical current, one would apply a heat current. And instead of measuring voltages to extract the electrical conductance, one would measure temperatures to extract the thermal conductance. Nevertheless, there is one very important conceptual difference between electrical transport in electronic topological phases like fractional quantum Hall states and thermal transport in chiral quantum spin liquids like the non-abelian Kitaev spin liquid. So in quantum Hall states, the only charge carriers in the system are the electron, and they are gapped in the bulk, which means that electrical conduction truly happens only along the edge. In contrast, in a chiral quantum spin liquid, the chiral Moiré edge mode is by far not the only heat carrier in the system. There are also all the acoustic bulk phonons, and we know from the experiments that the acoustic phonons are actually the dominant heat carriers in the system. After all, the longitudinal thermal conductivity found experimentally, which is due to the phonons, is 3 orders of magnitude larger than the thermal Hall conductivity that is attributed to the chiral Moiré mode. But then if there are all these acoustic phonons in the bulk, then they may lead to some kind of thermal bridge between the two chiral edge modes, even far away from the constrictions. And then one may worry that this kind of thermal coupling may actually wash away any interference signal that one would get. Also, while the edge phonon coupling is expected to be detrimental for the interference, at the same time, it's also necessary to observe the interference, because the kind of thermal leads and sensors that one would use in conventional thermal transport techniques would primarily couple to the phonons. And what that means is that if there is no edge phonon coupling, then the chiral Moiré edge mode will remain completely invisible from the perspective of the thermal transport experiments, even if it is present. So the main difficulty here is to reconcile anyonic edge interferometry that requires quantum coherent edge processes with conventional thermometry that instead relies on large-scale thermalization between the phonons and the Moiré edge mode. And our solution to this conceptual difficulty is to consider this unconventional device geometry, where 2 large macroscopic lobes are connected through a small mesoscopic central channel. Just for reference, the size of the lobes may be on the order of a millimeter, and the central channel may be on the order of a micron. And the purpose of the lobes is to facilitate effective thermalization between the chiral Moiré edge mode and the bulk phonons. And the central channel acts as a bottleneck for the bulk phonon transport, and therefore emphasizes the chiral edge transport. At the same time, due to its small size, it allows for coherent edge processes to take place inside. So in this kind of setup, one would heat one end of the device and cool the other end of the device. And then one would obtain the thermal conductance by dividing the heat current J, going from one end to the other end, with the temperature difference 2 delta T between the 2 ends of the device. And then, depending on the precise geometry of the central channel, whether it contains further constrictions in it or not, one can measure at least 3 different things. So in the simplest case, where the channel has no further constrictions, we show that under the right circumstances that I will explain later, the thermal conductance of the device is found to be equal to the same half-integer quantized thermal Hall conductivity that was seen in the current experiments. I should note that in 2 dimensions, thermal conductance and thermal conductivity have the same dimension, so this statement makes sense. But I really want to emphasize here is that in this kind of device setup, this half-integer quantized value, which is proportional to the half-integer chiral central charge, is not extracted from a small subdominant thermal Hall conductivity that appears on top of a 3 orders of magnitude larger longitudinal thermal conductivity, which, as I understand it correctly, is one of the main difficulties in extracting it correctly. But instead, it appears as the longitudinal thermal conductance of the entire device, the dominant thermal response of the entire system. So the main result here is that this kind of unconventional device geometry allows the extraction of the half-integer chiral central charge, which directly reflects the presence of non-abelian anyons in the bulk in a more reliable and accurate way. So if one has a single pinch point in the central channel, then anyons can start. So one could imagine that the edge modes come so close to each other that anyons can start tunneling directly. So for example, here the distance between the 2 edges would be on the order of 10 nanometers. So getting close to the scale of the lattice spacing. So in this case, there is a correction to the measured thermal conductance. And at the lowest temperatures, the dominant correction will follow this kind of universal power law with a highly non-trivial exponent. that reflects the tunneling of non-ionizing anyons between the two counterpropagating edges. And finally, if there are two constrictions, then this correction to the thermal conductance acquires an interference term that is sensitive to the number of non-trivial anyons, myronofermions, and or Ising anyons sitting in this central region in between the two constrictions. And what that means is that measuring the thermal conductance can detect individual anyons residing in this central region. So let me then now, in the rest of this talk, go through each of these three cases independently. But before I do that, let me explain how we actually compute the thermal transport in our system. So our formalism goes back to this earlier work with Mengsing, Lucille, and Leon, and also the related work by Yuval and Akim. So the idea here is that the heat in a chiral quantum spin liquid is carried by two completely different degrees of freedom. There is the chiral Moiré edge mode, and there are the bulk phonons. And at the lowest temperatures, the thermal coupling between these two degrees of freedom is strongly suppressed. And because of that, we define two separate temperatures, the edge temperature, which is only defined along the edge, corresponding to the chiral Moiré edge mode, and the bulk temperature corresponding to the phonon, which is defined everywhere. But the main point is that even at the edge where both of these quantities are well defined, they may be different from each other. So then we also consider three different types of heat currents in this system. There is the bulk heat current density, little jb here, denoted by black arrows, carried by the phonons. And if the phonons are assumed to be diffusive, then this heat current density is just proportional to minus temperature gradient of the phonons, with the coefficient kappa xx being the usual longitudinal thermal conductivity. Of course, in thermal equilibrium, by energy conservation, the divergence of this heat current density must be equal to 0. Now, these white arrows here correspond to the heat current carried by the edge, capital JE. Under very general considerations, this must be proportional to the second power of the edge temperature, with the coefficient here being a universal constant. But if then we assume an overall reference temperature T naught, so that any spatial variations of both the edge and bulk temperatures with respect to this overall temperature is much less than the overall temperature itself, then we can linearize our expression for the current in the temperatures. And then what we obtain is this simple form where J naught is just gamma T naught squared. And the coefficient of this linear term is nothing other than this half-integer quantized thermal Hall conductivity that was seen in the current experiments. So finally, there's also a third type of heat current, this exchange current density between the two degrees of freedom. So you can imagine, for example, if the edge myronofermions are hotter than the bulk phonons, then energy will flow from the edge mode into the phonons. And again, if we linearize everything in temperatures, then of course this exchange current density must be proportional to the just the temperature difference between the two degrees of freedom. But the coefficient here, importantly, can be a function of the overall temperature T naught. And what we find from a microscopic calculation in this paper is that it's proportional at lowest temperatures to the 6th power of temperature, which indeed verifies our original assumption that the thermal coupling between the two degrees of freedom is very, very strongly suppressed. Now, if I then take this equation, okay, and I should say that, of course, this exchange heat current density by energy conservation is equal to the minus derivative of the heat current carried by the edge. So if energy is leaking out of the edge, then of course the current carried by the edge decreases. And for the same reason, this exchange current density is equal to the normal component of the bulk heat current density. So if I then take this equation here, and I substitute my linearized expression for the edge current, then I obtain this equation for two temperatures. And what this tells me is that the edge temperature thermalizes with the bulk temperature at a length scale given by kappa xy over lambda. And this length scale, little l, which we call the edge bulk thermalization length, is of central importance in our work. Indeed, it's one of our essential assumptions that this edge bulk thermalization length is much longer than the size of the central channel to allow for coherent quantum coherence inside the central channel. But at the same time, it's much smaller than the size of the lobes to allow for effective thermalization inside the lobes. Our other fundamental assumption is that the half-integer quantized thermal Hall conductivity kappa xy is much less than the longitudinal thermal conductivity, which of course is very much satisfied in the experiments. So if these two conditions are met, then what happens is that each lobe has a constant temperature for both the edge mode and the bulk, and all the temperature drop between the two ends of the device happens in this central channel. Moreover, there are three independent heat currents in the central channel, the one carried by the top edge, the one carried by the bottom edge, and the one carried by the phonons. And we can even evaluate what these heat currents are. So the top edge, it comes from the right lobe, which is hotter. It has a temperature T naught plus delta T, which means it carries more heat. And if I go back to our linearized expression here, and I substitute T equals T naught plus delta T, then what I find is that the edge, the current carried by the top edge is J naught plus kappa xy times delta T. Conversely, the bottom edge comes from the left lobe, which is cooler, so it carries less current, and its current is given by J naught minus kappa xy delta T. Finally, for the phonons, I can just assume some kind of thermal conductance to be specified later. And then if this thermal conductance is kappa B, then the current carried by the phonons is just the conductance times the temperature difference between the two ends of the channel, which is 2 delta T. Then if I want to evaluate the thermal conductance of the entire device, this commodity kappa, I just add these 3 heat currents with the right sign structure, and then divide it with the overall temperature difference 2 delta T between the two ends of the device. And then what I get, not very surprisingly, is that it's just sum of kappa xy, the half-integer quantized thermal Hall conductivity, and the contribution kappa B coming from the phonons. And the main question is, what is this phonon thermal conductance kappa B? And here we need to make an assumption that the phonons are ballistic, which is the right assumption if both dimensions of the channel, the length and the width, are less than the phonon mean free path dph. Now we know from Professor Takagi's work that the phonon mean free path in ruthenium chloride already at a few kelvins is on the order of tens of microns. So if the channel is indeed micron sized, then these assumptions are very well met. And if the phonons are ballistic, at the lowest temperatures, where the width of the channel becomes less than the thermal phonon wavelengths, which for a channel width of about 100 nanometers would happen around 1 Kelvin, then most of the phonon modes are actually frozen out, and the phonon thermal transport also becomes quantized, because the only modes that can still be excited thermally are the Goldstone mode corresponding to like a uniform translations and rotation. And in this case, the phonon thermal conductance takes a value that's very similar to the half-integer quantized thermal Hall conductivity, with the only difference being that instead of the chiral central charge C, we have this small integer p, which is basically the number of phonon Goldstone modes. And we have reason to believe that this small integer p is equal to 4, but its value doesn't even matter as long as it is a small integer, as you will just see. So now if I then consider the thermal conductance per layer in an n-layer system, I get this formula here. And of course, the numerator here is just the thermal conductance of the entire n-layer system. And you may wonder why I'm multiplying kappa xy with n, but not multiplying kappa b with n. So the point is that the kappa xy comes from the spin liquid, and the spin liquid is two-dimensional. And each layer is its own spin liquid with its own chiral edge mode, and each of them contributes kappa xy individually. In contrast, the phonons are three-dimensional, so they can travel freely between the different layers. So the entire nanowire, the entire stack will contribute this value kappa b. So then if I plug in my expressions for kappa xy and kappa b, I get this final result for a thermal conductance per layer in an n-layer system. And now I can take two different limits. So first I can take the monolayer limit, which corresponds to n equals 1. In this case, the way I can find evidence for the half-integer chiral central charge, and hence non-abelian anyons in the bulk, is to take the experimentally measured thermal conductance, divide it with the overall temperature and with this universal constant, and find that the resulting number here, which is just c plus p, is half-integer rather than integer, which reflects the fact that in addition to the integer quantized phonon conductance, there is also half-integer quantized chiral edge conductance. So if instead we have a many-layer system where n is much bigger than 1, then of course the second term is negligible, and as previously advertised, the thermal conductance per layer just becomes this half-integer quantized thermal Hall conductivity. And again, I emphasize that in this setup, this is the dominant thermal response of the system and doesn't appear on top of something much larger. So then in the case of a single pinch geometry, at the pinch point, anyons can tunnel between the two edges and they can shuttle energy. And that means that we can define this kind of quantity beta, which basically tells us what fraction of energy is exchanged between the two edges as they meet at the pinch point. And in this case, the thermal conductance per layer in a many-layer system is no longer just the half-integer quantized thermal Hall conductivity kappa xy, but instead given by kappa xy times 1 minus beta. That makes perfect sense. After all, for beta equals 0, we just get back the previous case when there is no connection between the two edges. And if beta is equal to 1, that means that all the energy coming in from the right lobe just jumps to the other edge and goes back to the right lobe. The two lobes are disconnected, and so the thermal conductance between the two lobes must be 0. And this quantity beta, okay, that should be fine. This quantity beta can be calculated using conformal field theory. And what we find is that, not very surprisingly, the two most dominant processes contributing at low temperatures are the Majorana-fermion tunneling, which is a marginal perturbation, so it gives a constant behavior with temperature, and Ising-anyon tunneling, which is a relevant perturbation, so it gives a divergent contribution. And then, of course, the second one will dominate at the lowest temperatures. The total beta is just the sum of these two contributions. And then what I want to emphasize is that this non-trivial power law exponent 7/4 here, it basically comes from the conformal dimension of some operator in the edge CFT. So it's very specific to the given topological order and would be very difficult to reproduce from more mundane physics. And then finally, this is perhaps the most interesting case with 2 pinch points, in which case anyone can jump over at 2 pinch points. And this energy exchange fraction beta obtains an interference term that becomes sensitive to the number of bulk anyons in between. So to understand the nature of the interference, it is useful to realize that the longer path taken by the anyon jumping over this path is the product of the shorter path taken by the anyon this path times the anyon going around this loop. And what that means is that the ratio of the two amplitudes, which controls the nature of the interference, whether it's constructive or destructive, is given by whatever quantum phase is picked up as the edge anyon, which tunnels here, goes around this loop, encircling any bulk anyons that may be here. And that, of course, is precisely the idea of braiding. And so these phases picked up here will be precisely given by the braiding rules of the non-abelian Kitaev spin liquid. So let's start with the simplest case of Majorana-fermion tunneling. So in this case, the Majorana-fermion going around this loop is sensitive to the number of Ising anyons, because that's what it has a non-trivial braiding with. And it turns out that this interference term to this energy exchange fraction will just be proportional to the -1 times the number of Ising anyons, because the Majorana-fermion picks up a pi phase every time it goes around an Ising anyon. So basically, in this case, the interference will be constructive whenever there are even numbers of Ising anyons here, and destructive whenever there are odd numbers of Ising anyons. Now let's move on to the Ising anyon interference term, which is more complicated because Ising anyons have a non-trivial braiding with both Majorana-fermions and Ising anyons. And of course, it has the same temperature dependence as the Ising anyon tunneling itself, because it does come from Ising anyon tunneling in the end. So it's going to be the dominant contribution to the interference at lowest temperatures. And now, instead of maybe starting with the general case, it's instructive to start with the 3 simplest cases. So if there are no bulk anyons here, then of course there is nothing to braid around, so the interference will be constructive. The interference term is positive. Now if there is a Majorana-fermion sitting here, then an Ising anyon going around the Majorana-fermion picks up a -1 phase, just like a Majorana-fermion going around an Ising anyon would. So that means that this interference term becomes negative, and so the interference is destructive. And finally, if there is an Ising anyon sitting in the middle, then the braiding of an Ising anyon around an Ising anyon is interesting, because it doesn't just correspond to a complex phase factor, but instead it corresponds to a non-trivial rotation in this internal Hilbert space spanned by the Ising anyons themselves. And what that means is that the two outcomes are orthogonal, so they cannot interfere, and therefore the interference term is identically 0. And now the next thing to notice is that in fact these are the only 3 cases that one can obtain. So however I put in any numbers m psi and n sigma here, there will always be 3 outcomes, which makes perfect sense. After all, the non-abelian Kitaev spin liquid has only 3 topologically distinct anyon types. However, I can take any numbers of Majorana-fermions and Ising anyons here, and I start fusing them. And in the end, I can only get 3 end results: a net trivial boson corresponding to this case, a net Majorana-fermion corresponding to this case, and the net Ising anyon corresponding to this case. So in the end, measuring the thermal conductance of the device in this 2-pinch geometry will be sensitive to the total anyon content of this central region. And with that, I would like to thank you for your attention.
Interesting talk. Questions?
Gábor, could you, so this is just a basic question. Could you show maybe the last slide on the 2-pinch construction? Yeah. So how do I understand the negative sign of the thermal conductivity? I mean, I understand that when you talk about Aronoff-Bohm effect and the cancellation of the paths, right, you could have destructive interference. But if I'm applying gradient of temperatures, let's say from the left to the right, how can I get the negative current?
This is just a correction to the thermal conductance that is on top of a large positive contribution. So it's just a change with respect to the overall value.
But let's say,
so it would never become negative. So I mean, here there is a weird thing that if you just take this at face value, and of course this one becomes divergent at low temperature. So this one would become negative. So at that point, okay. So I should say that this thing came out of a perturbation theory. So there will be a temperature range within which this is valid. If you reduce the temperature at some point, the perturbation theory breaks down, and basically because Ising anyon tunneling is a relevant perturbation, your whole bar will split in two. At that point on, the conductivity will pretty much go down to zero, and all of this what I'm saying here will no longer be valid. So there is a temperature range in which this will be true.
Mm-hmm. And qualitative question, the reason you're ignoring phonons fundamentally is because the construction, the reason you can ignore the phonon conductivity is because the construction is very narrow compared to the
so the entire central region is very, very small. And there is this length scale which determines on what length scales you have a significant thermal coupling between phonons and Majorana fermions. And if your central region is much smaller than that length scale, then at that point the phonons are there, but they will not talk to your Majorana edge mode. So the Majorana edge mode can be thought of as an independent edge mode, like in the kind of simplest possible picture.
Other questions?
So you mentioned you did a CFT calculation to get the fractional power.
Yes.
So what calculation are you doing?
Yeah, so it's basically perturbation theory. So you evaluate some Majorana Green's function along one of the edges, and then you treat the two edges independently from each other, which kind of makes sense because they're connected through this very long lobe. So at that point, there is no quantum coherence between them. And then you just write down the Majorana fermion and Ising anyon tunnel links here. You find that at first order you get nothing because you get like an odd number of operator on each of the edges. So that just gives 0. But then at second order you get something. So you get like a 2-point correlator at the bottom edge and a 4-point correlator at the top edge. They can all be evaluated in CFT in standard ways. And then it just gives you. But you know, ultimately this power 7 over 4 just comes from the conformal dimensions of the Ising anyon. So I think the general formula would be 2 minus 4 times conformal dimension, and I think it's conformal dimension is 1 over 16 for the Ising anyon. So 2 minus 4 times 1 over 16 is 7 over 4. And for the Majorana fermions you will get 0 from the same argument.
So my question and comment is only because you used fractional quantum Hall analogy to motivate, and also the conformal field theory is very similar, if not identical.
Yes,
okay.
yes. That's true.
And you are trying to motivate experiment, okay? So I see two huge disadvantages. One is that in the fractional quantum Hall case, we know what to look because there is a 5-half fractional quantum Hall plateau. And then, you know, that's why we have to do the interferometry. And Bob Willett has been doing it for now 20 years. With, you know, people of goodwill could disagree, but not any conclusive result. With no problem of phonons, it's just electronic interference. And so this is a huge challenge, right? And I have no problem with the theory.
I'm not saying this is easy.
Myself, okay? So if I were an experimentalist, what did you tell me? I mean, because as you know, in the quantum Hall thing, people are thinking about purely measurement-induced braiding. Nobody's thinking about interferometry in the context of actual devices. So, and because it didn't work.
Well, I mean, Mike Mumford did see the effect of braiding in fractional quantum Hall, and what I would say is, okay, the thermal transport in neutral systems has one advantage, is that you don't need to worry about charging energy. So I'm reading Mike's papers. It's always one of the biggest issues is that they want to reduce the size of the arm of their interferometer, because of course if it's too long then your interferometry will be washed out by thermal effects. So they need to keep it small, but if they make it too small, then charging effects become important. And then those lead to some spurious things. So here there are no charging effects because it's charge neutral.
Okay, so
that's one silver lining, I guess.
So you have an exponentially small advantage, but you have an exponentially large disadvantage of phonons. Okay, so even in even in Manfra's experiment, this Febvre-Perot experiment doesn't really see the statistical phase. It's cannot tell you the statistics. It can't even distinguish between fermions and bosons. So there are many issues that I'm actually intrigued. This is a very good idea. But I don't know what to tell an experimentalist given the situation in 5-hub. I'm not trying to discourage you. I'm truly perplexed.
I mean, ultimately, I think that the long-term goal would be to. So this work is to understand how you can achieve thermal anyon interferometry using conventional thermal transport techniques. So I think ultimately what we need is different kind of thermal transport techniques where the thermal leads and sensors can couple directly to the Moiré edge mode. And then you don't need these large bulky lobes to have thermalization with the phonons, which is, I think, is the biggest issue. And also with the thermal transport experiments that's the reason that even if there is a Moiré edge mode, the thermal hole conductivity will go down to 0 at lowest temperatures because there is just no edge phonon coupling at that point. So if you could get rid of the phonons as the middleman, I think that would make this much more feasible.
Any other questions? If not, let's thank Gábor and all the speakers of the morning session.